There is a new alien language that uses the English alphabet. However, the order of the letters is unknown to you. You are given a list of strings words from the alien's new language dictionary. Now, it is claims that the strings in words are sorted lexicographically by the rules of this new language. If this claim is incorrect, and the given arrangement of strings in words cannot correspond to any of the letters, return the empty string. Otherwise, return a string of the unique letters sorted in lexicographically increasing order by the new language's rules. If there are multiple solutions, return any of them. So all this really means is that we're given some list of words, which we're assuming is correct in its lexicographical order. And we want to try and figure out the correct order of the alien's alphabet. It doesn't have to be all the letters in the alien alphabet, but we want to know what's the correct order of them. It's kind of like saying if we had this list of strings, if we're talking about the English alphabet, we can figure out that the correct order of these letters would be A, C, G, and S. We don't know the entire alphabet where it's a B, C, D, all the way to X, Y, Z. We're only able to figure out these ones. And suppose we switched string with Google. Let's say this was some sort of alien dictionary that happened to use all the same words that we do. The correct order of these letters then would be A, C, SG. So we'd swap these last two letters. So our goal is to get this string based on our words. However, we do have that one case where, let's say, app appeared at the very end of this. Based on this, we'd have A also appearing at the end, and we know that this couldn't possibly happen. So instead of returning this, we would just return the empty string instead. So now, how the heck do we approach this problem? We were given this for our first example, but let's start off with an easier problem. So let's just say we had W, E, and R first. We can tell that the W has to come before the E, and the E has to come before the R. Again, this is assuming that the W, E, and R are already in the lexicographically correct order. What if we had something like this? Something like WX and WY. Well, in this case, we recognize that the W's are the same. So the W and the W. So we have to defer to the next letter, so the X and the Y. And we can say that there's going to be a relation between the X and the Y. So the X and Y. So we're starting to build up and get an idea of how this actually is supposed to look. But how are we going to represent this? We said before that the W and the E have to come before each other. So let's actually represent this as like a graph. So we can say W has to go before the E. We saw the X has to come before the Y. So let's just say X has to come before Y. This E has to come before this R. So E and then R. And now let's think of a way to actually break this. And what would this look like in our graph? So if we had a W at the very end of this, we know that W appeared before. So we know that this can't be a situation that will return us something that's not the empty string. So we can look at this and we can say the R has to come before the W in this case. And that would look like this. So now looking at this, we have a cycle. And then there we go. This problem just comes down to cycle detection. If you haven't checked out my video on course schedules, this is pretty much exactly what we went over. The biggest part of this problem is just going to be what do we need to do to set up our graph? And then how do we use Kahn's algorithm to look for cycles within our graph? So before we move on, let's just figure out our first given example. The key to building a graph is looking at the current word and our next word and saying what information can we derive from this. So between our first word and our second word, we see that we have this W and this R the same. And again, assuming that this is in lexicographical order, we can say that this T and this F have a relation to one another. The T has to come before the F. Between our second and third word, that's easy. Assuming this is in lexicographical order, we just have to look at this W and this E, and we can say that our W comes before our E. Looking between the third and the fourth, we share this E. So we're just going to look at this R and this T, and we know that we have a relation. The R comes before the T, so R becomes before the T. Looking at our last one, we know that this E has to come before this R. E, R, so we say this E comes before this R. And then, like our course schedule problem, it just comes down to iterating over our graph. We start at any node that does not have any incoming edges. So we start at this W, we'll mark it down as well. So W, E, R, T, F. We didn't encounter any cycles, so this would be our answer. And if we look back at the output for our first example, it looks like we had gotten the right answer. All right, let's start coding up our solution. But before that, if you've been enjoying the video so far, please consider giving a like and subscribe. It really helps grow the channel. So just like our course schedule problem, we're going to be using an edge list to represent our graph, as well as an incoming list to tell us how many edges are going into a node. So let's start setting up our graph. We're going to iterate over all words except for the last one, just because we're going to be considering the first and the next words. We're going to represent that with first and second word, and we're going to look between the characters of the different word. The first non-similar character is where we draw our relation. Remember, while looking at two different words, the only thing that we care about is the first non-similar one. That's the only thing that's lexicographically significant between the two words. So we iterate over the characters, taking the minimum of the shorter length word, and we say the first non-similar character between the two, that's our relation. So we call this our source and our destination. We append it to the edge list. Remember, our edge list is just going to be a node that points to a list of other nodes. This list of nodes is just going to be our neighbor. And every time we point to a new destination, we increase that destination's incoming edges in our incoming dictionary. And then we have to break. Because again, the only lexicographically significant character between our two different words is the first one that's different. Anything that's after that doesn't matter. So now that we have our graph set up, we can begin to fill out our queue. So to fill out our queue, let's first create a set. This is just going to be a set of all letters that we encounter in our graph. So to do that, we're just going to iterate over all the words and then iterate over all the characters in each word and then add those to a set. You can think of a set as just a list of characters, except each unique character only appears once. So let's just move some of these things out of the way. While our queue is not empty, we're going to get the next node from the queue. Let's also add an answer string, just something that we're going to keep appending to. And every time we pop, and every time we see a new character, we're just going to add that character to the answer string. So now that we popped our node, let's actually remove this from the graph. So we're going to say for node in edge list node. Let's actually call this destination and this source. Let's remove an edge from our destination node. And if we remove all incoming edges from our destination node, we're going to add our destination node to our no incoming queue. So we repeat this process until we remove all nodes from our graph or we detect a cycle. So then finally we can say return answer, but only if we detect that we have the same length of characters between our answer string and our all set. Remember, this is just the set of all the characters that we have encountered. If this isn't the case, we're just going to return the empty string. Let's see if this runs. So this is supposed to be source as well. And even though we had built this list of words, we actually totally forgot to initialize our queue. So let's do that now. So for each character in our set, we're just going to check if that character is in our incoming dictionary. If it's not, we're just going to add it to our no incoming queue. Now let's see if this runs. All right, nice. Let's submit. So this is an edge case that doesn't have to do anything with what we were talking about before, anything about topological sort or anything like that. This is just a rule of how to order words lexicographically. If we have the same letters between two different words, the word with a shorter length needs to appear first. This is just a weird edge case that I wanted to leave towards the end of it, since it didn't really have to do too much with the rest of the problem. So for this one, all we have to do is just look between all first and next words. If they all have the same letters, but the next one is shorter, then we'll return false. So that's going to look like iterate over all words except for the last one. Let's just call words I the first word, words I plus 1 the second word. If the length of the first word is less than the length of the second word, then we should check to see if they have the same letters. So we're just going to iterate over the length of the second word. And if we encounter any letters that are different, then we know we're not in this case where they'll have all the same letters. So we're just going to break out of this. Otherwise, if we've gotten through all of our letters, we're at the last letter, and the last letter again is the same, we're going to return the empty string because the words that were given in our alien dictionary are not in lexicographical order. All right, let's run this. Let's submit. And there we go. Like, subscribe. A link to the code will be in the description. Join our Discord for some extra help, problem suggestions, and announcements, and I'll see you in the next one.